Alright, this is gonna be 8.3. I'm gonna skip the do now just to save me time. And let's kind of get through this as quick as possible. So let's talk about phase waves. Now, waves represent cyclical patterns, right? Repeating patterns. And we can kind of represent a wave in terms of a circle. Right? As you can see in this GIF, in this top GIF right here, well, you start at 0. Well, I'll wait for it to loop again. So essentially, you're starting at 0, going to 90, to 180, to 270, to 360, to 90, and 80, 270, and 360 again. Right, and essentially what you're doing here, well, this represents 0 degrees, right? So then it goes up, and then this represents 90 degrees, and then this represents 180, 270, right? And then so on and so forth. So that's 360. Now, here's the thing. Oh, I'm sorry. That's not 360. There's something here in the middle, obviously. So this would be 360, right? And so this would be 450. It would be 450 degrees. And this would be 540 degrees, and this would be 630 degrees, and this would be 720 degrees. And so, well, there are two wave cycles here, and thus, well, right, so there are two wave cycles here, and so that's why it's 720. If it was just one wave cycle, where, well, it would just be 360, right? 360 degrees, as represented on the bottom image over here. And so those are the parts of the wave we label as degrees, right? Those are our phases. Those are our phases. And well, why is that important? Right? Why do we need to assign a phase to certain parts of the wave? Well, let's take a look at this slide, right? Let's take a look here. Well, now here, right? So our waves are in phase. Well, rather, if you take a look at this image right here, well, both of these waves, there are two waves here if you can't tell. There's a red wave and a blue wave. So both of these waves are at 0 degrees. And both of the crests kind of peak at the same position, right? So they're both at 90 degrees. Both of these waves have their crests at 90 degrees, and both of these waves have their crests at 270 degrees. And same thing with 180, right? So 180 is there, and then 360 is there, and so they kind of both line up. They both match. They both line up. So now, and so we can say that both of these waves are in phase, right? So they have the same crest at the same time, right? And so rather same position, and troughs at the same position. Well, they both peak at the same point. On the other hand, well, if you kind of take a look at this, right? So here it's 0 degrees, and here it's 90. And over here it starts at 0, and here, well, I'm not gonna put that part, but you get the point, right? So this second line right here, well, it's 0 degrees over here. And for the first line, the red line, 0 degrees is over here. And so, well, clearly we see that the waves are not matching up. Where my blue line, where my second wave is 0 degrees, my first wave is at 90 degrees. And so we can say that these two waves are out of phase. Well, how do we measure how far out of phase are they? Well, we can say that, well, clearly this first line and the second line are 90 degrees out of phase, right? Because where my second line is 0 degrees, my first line is 90 degrees, and so they are 90 degrees apart, and so they're 90 degrees out of phase, right? So here, what are the points on the wave diagram below? Well, which points on the wave diagram below are 90 degrees out of phase with each other? And then when we talked about, well, hold on, I need to sketch this. So here A would be 0 degrees, right? A would be 0 degrees, B would be 90 degrees, and this would be 180. This would be 270, 360. C would be, if we were following proper, this would be 450, 540, 630, 720, right? So which 2 points on the wave diagram below are 90 degrees out of phase? So which 2 points are 90 degrees apart? Well, clearly A and B are 90 degrees apart. So A and B are 90 degrees apart. Well, what other 2 points are 90 degrees apart? Well, also D and E, right? Because, well, if you do 720 minus 630, clearly you get 90 degrees. And so here we have two other points that are also out of phase, D and E. So to B, which point on the wave is 90 degrees out of phase with point P? And again, if you kind of just label it, this would be 0, this would be 90, this would be 180, this would be 270. And we don't even need to go further because clearly if you do B minus P, which is 270 minus 180, you get 90 degrees. All right. And so it's point B. So which point on the wave is 90 degrees out of phase? Point B is 90 degrees out of phase. So now we talk about interference, right? We talk about superposition now. So let's take a look at the top GIF right here. And let's look at the top GIF. So you have two waves. Actually, here I'm gonna take a snapshot of this. So here you have two waves going towards each other, right? So you have a wave that's going this way and another wave that's going this way. And so they both have separate amplitudes. And so they come together, they hit each other, and what happens is that they do something that we call constructive interference. Well, what does that mean, right? Well, all that means is essentially that they're adding their amplitudes, right? So you have constructive interference, and constructive interference happens when the two crests when two waves add up to their maximum amplitude. And so you have constructive interference here, and clearly you can see that, well, both of these waves add up and they kind of form a much larger amplitude. And now destructive interference, on the other hand, well, essentially is when, well, hold on, let me just take a new picture. When they kind of cancel each other out, they're out of phase waves, right? So you have these two right here, opposite amplitudes, and well, when they combine, clearly you kind of see like a flat line, right? They're essentially canceling each other out when the waves hit each other, and we call it destructive interference. Call it destructive, right? So there's constructive and destructive, and both of these are known as superposition, wave superposition. And you can kind of see it over here, right? So this green line, this blue line and green line, they add up. When they add up here, there's constructive interference. And now when they, over here on the right hand side, the blue line and the green line, they kind of cancel each other out. And that's destructive. So watch it again here, right? Over here, that's destructive. And this is another example of constructive interference in real life. Let me just mute this. Let me see. Let me go to the point where it is. I think it's right here. So what's happening here is that you see wave generators on the outline of this pool, right? So you have a giant pool and you have wave generators on the outside. And so what they do is they vibrate back and forth, creating a wave, thereby their name being wave generators. And so they're generating this wave, and what you're gonna see in this video, is that each of these waves kind of, they don't have much amplitude, but they are there. And so you have successive waves that are gonna go towards the center, and the center is, I don't know, somewhere, but this is kind of just an example. So we're gonna go towards the center. Now each of these waves, right? Each of these waves, they kind of have an amplitude, right? So all of these waves have an amplitude, and the amplitude is kind of getting larger and larger and larger as the wave goes towards the center, right? Because the area of this circle, right, is clearly getting smaller, and thus they're kind of condensing. All these waves are combining, they're adding on to each other, and their amplitudes are getting larger and larger and larger. And then something happens at the middle. Well, what happens when you have all these waves converge on a singular point? Well, all their amplitudes are going to add up, and the wave is going to go all the way up, right? Because you have all their amplitudes combined. So that's what you're going to see in this video. And they have a larger wave, and so the entire wave, they kind of just combine their amplitudes in the middle, and you see this water shooting up, right? And so that's an example of constructive interference. So now let's move on to this example problem. So which diagram best represents the resultant pulse at the instant the pulses are passing through each other? Right, clearly this pulse is moving this way, this pulse is moving this way. This is, I don't know, an amplitude of that. So let's say it has a positive amplitude, this is a negative amplitude. When they meet in the middle, well, what happens? Clearly they're just gonna add to each other, right? So this, obviously this, the second one is larger than the first one, so it's gonna overshadow this one. So when they combine, you kind of get this negative amplitude over here. And the answer that most closely resembles that is B. Right, you're adding them. Right, so you're adding this wave, you're adding this wave. Clearly, this is gonna get canceled out by this, and so you're left with just the other half. You're adding them. Like this would be +1, and this would be -2. Well, if you add them, well, you get -1, and then, well, that's this wave. So here, so the superposition of waves produces the greatest positive displacement V from its rest position at which point? So again, 0 is its rest position. So 0 is your rest position, right? If you were to add both of these waves, so this would be at point 2, right here at point A. So this would be at point 2, this wave is at point 2, this wave is at point 1. If you add both of these waves, well, you're going to get 0.3, an amplitude of 0.3. At point B, you add 0.2 and then -0.1. And so you're going to get an amplitude of 0.1. C, you have an amplitude of +0.1, -0.2. So you have an amplitude of -0.1. So now, -0.1 plus -0.2, that gives me -0.3. All right. And so the question says, which waves produce the greatest positive displacement? Well, it's going to produce at position A. Right? At point A, you're going to get the greatest positive displacement because you get 0.3. All right. You're essentially adding the waves. That's all you're doing. So you have two periodic waves. So what's being shown here is something called standing waves. Right, this is something called standing waves right here. Well, standing waves happen, so let's look at the bottom here. Standing waves occur when two waves are moving in opposite directions, right, as indicated by the red and blue line on the bottom. So they're moving in opposite directions with the same amplitude and the same frequency. And well, when that happens, you see something called a standing wave as shown in the top GIF. And in a standing wave, we label points, and we call certain points nodes or antinodes. And so nodes are here, right? So nodes are essentially the location of total destructive interference. That's essentially where you're going to have no amplitude at all. And antinodes, right? So this is one antinode, this is two antinodes, this is three antinodes, 4, 5, 6. These are 6 antinodes here. There's 6 antinodes here. And antinodes are essentially, well, when these two waves, right, this red and blue wave, when they combine and create the maximum constructive interference. Whoa, what happened here? That's when they combine and create your maximum constructive interference. Right, you're essentially seeing the greatest amplitude possible between these two waves. So there are 6 antinodes here, and there are 7 nodes. So again, take care to remember the definition of antinode, right? So antinode is the location of total constructive interference. So then this GIF right here shows standing waves in real life, right? So you have a spring, so you have standing waves right here, back and forth, back and forth, back and forth, back and forth. And so this one shows it in real life as well. So it's in a rectangular pool this time, and you see waves being, you essentially see a standing wave, multiple standing waves actually. Multiple standing waves, okay. Let's do a practice problem. The question says, well, how many antinodes are shown in the standing wave? Again, antinodes are places of constructive interference, meaning here, here, and here. So there's 1 antinode, 2 antinodes, 3 antinodes. Right, so there are 3 antinodes. If the question was asking you for nodes, well, this would be a node, this would be a node, right? Because this is where essentially where there's essentially no amplitude, and this would be a node. So there are 4 nodes here. There are 3 antinodes and 4 nodes. This question, on the other hand, is asking you maximum constructive interference occurs at which points? Now, when the question says maximum constructive interference, they're essentially referencing antinodes. Right? Antinodes are where constructive interference takes place to get your max amplitude. So we're looking for antinodes. B is an antinode, D is an antinode. So antinodes B and D. And these places are antinodes, right? So these are antinodes, and A, C, and E are nodes. All right, cool.